Hi, this is Hillol Kargupta, and welcome to our part three series on distributed machine learning. So today we are going to talk about distributed inner product computation, you know, and which is used in many different applications of machine learning, including uh, attention, clustering, and a whole bunch of other things. And we'll talk about all those things in a minute. So let's get started. All right. To start with, let's talk about inner product. What is it? Why is it important? Let's talk about this. So, inner product is a simple, algebraic quantity, and which is frequently used in many different disciplines, for lots of different things. So, inner product is usually computed between two vectors, and given two vectors x and y, it's essentially generates a scalar quantity, which is xi times yi summation over I. Now that's the algebraic definition of the inner product between two vectors. You can extend that and generalize that to matrix computation. Um, but what does it really mean? You know, so many of you are probably familiar with vector spaces. Essentially, a vector space is a collection of objects or vectors, that support some properties like addition, scalar multiplication, things like that. And if you want to sort of physically understand what it means, consider just a map. And uh, in a map, if you want to sort of draw the analogy to vector space, it's basically the vector space correspond to kind of things like locations and that sort of stuff. On the other hand, inner product is a vector space where um, this uh, quantity inner product is defined. So inner product in a vector space, like a map, would typically correspond to things like similarities and angles, that sort of stuff. So that's what inner product is. And now the question is, why do we care about inner product, right? Why bother? Now, since we are talking about distributed machine learning here, let's focus on applications of inner product computation in machine learning in general. So in fact, it shows up almost everywhere in machine learning. You know, um, inner product computation is fundamentally connected with the notion of distance. And for example, if you're trying to compute Euclidean distance, Euclidean distance computation can be easily posed as an inner product computation problem. So it's important for that. And if you're trying to do distance computation, and which is used in clustering, outlier detection, you name it, you know, um, inner product preservation is often used in representation construction. For example, if you're doing principal component analysis, which basically takes the covariance matrix, and to do the eigenanalysis, compute eigenvectors, eigenvalues, and essentially project the original embedding to this, the space spanned by the eigenvectors, and um, and similarly, Fourier transformation. That's also another example of an orthogonal transformation, and both of them, eigenvector transformation, Fourier transformation, all of them preserve inner product. The kernel trick, if you're familiar with support vector machines, the kernel trick essentially allows you to compute the inner product in a high-dimensional space without having to construct the high-dimensional space explicitly. So in a Mercer's theorem, for example, provides some elegant results supporting this kernel trick. So inner product shows up in support vector machines, clustering, outlier detection, and in fact, like these days, deep learning is quite popular. And one of the popular architecture for deep learning is the transformer. And in the transformer architecture, one of the key component, is the attention, the self-attention, module, for LLMs, large language models. And attention scores are essentially computed based on inner product. So inner product is almost ubiquitous in machine learning. All right. So now let's move to the next slide. We're going to talk about distributed inner product computation. And why do we care about that? First of all, if you're trying to scale up machine learning, if you're trying to do deep learning, for example, and you want to compute the attention score in a parallel distributed manner and scale up that, then you should be interested in this. Distributed inner product computation is also used in other fields, for example, quantum computing. And in quantum computing, if you're trying to compare two states, then typically distributed inner product computation algorithms are used, using varieties of sampling techniques and other techniques, like polysampling and stuff like that. And one thing I haven't mentioned here is like, if you are interested in privacy preserving data mining, distributed inner product computation is also used over there. For example, using secure multi-party computation, SMC techniques, inner product is computed in a distributed manner. And in this session, in this part, I'm not going to talk about privacy preserving data mining or privacy preserving machine learning explicitly. So I'm going to primarily focus on communication efficient algorithms for distributed inner product computation, with the primary objective of scaling up machine learning in a distributed environment. So now, what do we really mean by distributed inner product computation? Let's make it a little bit more precise. Now, as you saw in the previous slide, inner product computation is essentially sum of different scalar components, xi times yi, right? So it's decomposable, and it's additively decomposable, to be precise. So if your data set is kind of so-called horizontally partitioned, in other words, each side observes the same feature, but different parts of it, different observations. So in that case, like the solution is fairly trivial. Like let's say you have n observations. It's an n-dimensional feature vector space, and first k observations are made at site 1, and the rest of them are observed at site 2. For a simple example, in that case, you can just compute the partial sum at site 1 and partial sum at site 2, and send the scalars, add them up, and you get the inner product. So that's trivial. It becomes more challenging when the different sites observe different features. All right. So, for example, if site 1 observes feature x1 and site 2 observes feature x2, and each of them are column vectors, for example, and you're trying to compute x1 dot y, x1 dot x2, and you're not allowed to ship the data completely, because that beats the whole purpose. Like is going to be, you want to create a communication efficient way to compute that inner product. So there are like different types of algorithms for that. For example, deterministic algorithms. We'll talk about that. And then, probabilistic sketch-based algorithms. We are also going to talk about ordinal algorithms. So I'm going to explain, what they are. They're fundamentally order statistics-based approaches. So we're going to talk about these three and a few other stuff. So let's move on to the next slide. So this one talks about deterministic techniques, right? So the idea is, you have these two sites. Site one has this A1, A2 through AN. This is a column vector. And site two has this B1 through Bn. This is another column vector. And you want to compute the inner product between these two. Now, the core idea is that if you don't want to send the entire vector from one side to another side, then you have to figure out what is really needed for that, for accurate estimation of the inner product. So, for example, if you're dealing with time series data, you may want to consider orthogonal transformations that preserve inner products, like Fourier, wavelets, things like that. Eigen decomposition, or so fundamentally, you have to pick up a representation in a basis set where the data is kind of the salient features in the data are extracted, and that's basically the sense. So, for example, if you compute the Fourier transformation of A1 through AN, and to pick up the significant Fourier coefficients, send those to the other side, and in the Fourier domain, you can since it's an orthogonal transformation, you can compute the inner product, and Fourier transformation is inner product preserving. So you got the inner product. So there are varieties of techniques for extracting salient features from the data, and then using orthogonal transformations, for example, and computing the inner product. So the general approach is that transform the data vectors, communicate the sufficient statistics, and compute the inner product. All right. Now let's consider an example of a probabilistic approach. So you have these two nodes, node 1 and node 2. Just like the previous slide, node 1 has this column vector A1 through AN, and node 2 has this column vector B1 through Bn. And we want to compute the inner product in a communication efficient way. A simple example of this would be the following. That I would have a common random seed generator, that you can do by just simply generating a single random seed, and it's a scalar number, and make sure that both the nodes have the same number, random seed generator, and then generate these random numbers. What are you going to do with that? You are going to flip a coin and change the sign of each of the entries in the column vector. So, for example, A1, with 0.5 probability, you're going to keep the current sign, and 0.5 probability, you're going to flip the sign to the negative of them. So, which is equivalent to taking AI and multiplying that by a scalar ji, where ji takes a value from the set +1 or -1 with uniform probability. And then after you flip the signs uniformly, you add them up, compute a scalar, and we call it z1k, for example. You do the same thing at the node 2, compute z2k. So you get two scalars, and now you share the scalar and multiply that z1k times z2k. So you compute that product and repeat the same thing a few times, take an average of this scalar product, and that will be an estimate of the inner product. So this is fundamentally based on Johnson-Linde stress theorem, and it basically exploits the fact that large random vectors are almost orthogonal to each other, almost, okay, on average. So that's in an example of a sketch-based technique. And this graph kind of shows that the data kind of comes down, and so so this is an example of a probabilistic randomized technique for computing inner product. I'm kind of explaining these things using a two-node scenario, so that it's easy to understand, but it's going to be easily extended to a multi-node scenario. And people have done that. There exists a body of literature on that. Okay. All right. So now let's talk about a slightly different kind of approach. I call it an ordinal approach. So think of the following problem. Let's say instead of directly estimating the inner product value, I'm interested in the computation of a set of inner products. For example, inner product matrix. For a given data set X, you're trying to compute XX transpose and which is the inner product matrix. But instead of estimating each of these entries, you wanna identify the significant one. So what if I just simply ordered all the entries of the inner product matrix and sort them and pick up the top ones? So we wanna, without having to explicitly compute all of them, I would rather like to identify quickly the top ones and maybe just exactly compute those. So how do you do that? So consider the following problem. Let's say I make you stand with your two hands apart, and I give you a set of books in each of these hands. They're not necessarily same number of books. Now, if I ask you which one weighs how much, so for example, the stack of books that you have on your left hand, how much does it weigh? Or if I ask you the pile of books that you have on your right hand, how much does it weigh? Most people will kind of struggle to answer that unless they're really expert in weights and that sort of stuff. Now, if I ask you which one weighs lighter or which one weighs heavier, most people will be able to answer that easily. So that's the idea, that constructing an order, maybe a partial order or a linear order, may be easier in some cases compared to actually estimating the random variable systems. There exists a body of literature on order statistics, which essentially explores estimation of ordering, relative ordering. If I give you a set of random variables, instead of directly estimating the random variables themselves, you consider the order, the relative order between a pair of random variable as a random variable, and try to estimate the order. The field of order statistics, explores that. I learned order statistics, when I was a graduate student, from David's book, and so if you're new to that, you can check it out. And there exists a body of literature on finding top k entries in the inner product matrix using order statistics-based techniques. Kamalika Das and Liu and myself worked on this approach in my lab at UMBC, and the paper is cited over here. So that's another approach. If you're interested in identifying the top k elements of the inner product matrix, you could use order statistics-based techniques to estimate the the significant entries of the inner products without having to compute the entire inner product matrix explicitly. All right. So next, I'm going to spend a few minutes on comparing discrete structures and using distributed inner product computation algorithms. So inner product in the function space, right? So is a function space, so we are talking about space, where, which is a collection of objects, and those objects represent functions. Okay. And we want to compare functions. Now, function representation can be complex, and it could have a very large description, exponential complexity description. So comparing, functions may not be that easy. On the other hand, for some classes of functions, we may be able to compare using distributed inner product computation algorithms efficiently. For example, decision trees of bounded depths can be compared efficiently using inner products. Let's see. So one way to do that would be to compute the Fourier spectra of the tree. So a decision tree is essentially a function. So in general, we are talking about the class of functions that can be represented using a tree-like structure. All right. So a decision tree is essentially a function, and so you can compute the Fourier representation of that. So there exist some papers on that, Kushlevitz and Mansoor, Park, Agari and Kargupta, myself in my lab, they worked on that. So so essentially f of x can be represented as a weighted summation of the Fourier basis functions. All right. If your domain is binary, then this Fourier basis reduces to a special case of Haar functions, Walsh functions, but in general, the Fourier basis functions can be used to represent a tree-like function. So let's look at some of the properties which basically makes the inner product computation for decision trees very efficient. Number one, the Fourier spectra of functions that can be represented by trees, is very sparse. It has only polynomial number of non-zero coefficients. If as long as the depth of the tree is bounded. If k is a depth, then all coefficients involving more than k features are zero. All right. So that's good to know. Moreover, the higher order coefficients that basically depend on multiple features, the higher order coefficients are exponentially smaller compared to the lower order coefficients. So that means, like, if you want to approximate a decision tree in the Fourier representation, then you may be able to neglect some of the higher order Fourier coefficients. So that's good. And so basically, the tree has a polynomial representation, complexity representation, and it can be approximated by the low order Fourier coefficients. So that allows us to efficiently represent a decision tree in the Fourier domain. And since Fourier is an orthogonal transformation, it also preserves inner product. So you can actually compute the inner product of trees. So if f1x and f2x are two trees, and w1 and w2 be the corresponding Fourier spectra, then the inner product of these two trees, f1 and f2, is equal to the inner product between the Fourier spectra of these two trees. So this is what the inner product preservation means. And you can, generalize this and extend this stuff to other interesting things like orthogonal decision trees. So if you can compute uh, the inner product in the Fourier space, and you can compute covariance, and you can do principal component analysis of that, and you can also go back and forth from the Fourier to from the tree to Fourier representation, and the Fourier representation to tree. And since the eigenvectors are essentially linear combination of these columns of Fourier coefficients, each representing a tree, so the eigenvector itself is a Fourier spectra, and from there you can also compute the tree. Go back there. So so this efficient representation can be used for computing the inner product, comparing trees, and to do other fancy interesting stuff like the orthogonal trees. So and you can use the distributed inner product computation algorithms like the ones that we described earlier for comparing discrete structures and essentially performing an algebra of discrete structures like decision trees efficiently. All right. So finally, the conclusions. So item number one, inner product computation is almost ubiquitous, and many machine learning algorithms can be reduced to computing a set of primitive operations such as the inner product. All right. So if you're trying to construct a distributed algorithm for machine learning, so your one way to approach that is that, okay, here is the operation that we need to perform, for example, attention, and then say, okay, what are the computational tasks that I have, and how can we reduce this task to some of the basic primitive computation? Often it turns out that they boil down to some simple computation like inner product computation, L2 norm computation, things like that. And second item is the distributed inner product computation algorithms for sites observing different features usually involve computing summary statistics and estimating the inner product based on that. All right. And the final item that we covered is that the inner products between discrete structures, such as functions that can be represented as trees, like the decision trees, can also be efficiently computed. All right. So here are some references that we talked about in this presentation. So you have to refer to this and dig a little deeper if you're interested further in any of these techniques. And finally, thank you for your attention, and more stuff are coming soon on distributed machine learning. So please stay tuned, and we'll be back. Thank you very much.